All right, let's dive in. Today, we're going to break down two concepts in electricity that you see everywhere but maybe don't think about too much: potential difference and power. Let's get right to it.
So, you've definitely seen this before. You pick up a light bulb, and it says 60 watts. Your microwave might be 1,000 watts. It's a power rating, sure, but what is power really? Like, in an electrical sense, what's a watt actually measuring? That's the little mystery we're going to solve today.
Okay, before we even touch a single wire, let's get a handle on what power itself means. Just imagine you're pushing a really heavy box across the floor. The effort, the energy you spend to move it, that's what physicists call work. Now, power is just how fast you're doing that work. Pushing that box across the room in 10 seconds takes way more power than doing it over a whole minute. See? It's all about energy over time. And when we're talking units, 1 watt is simply 1 joule of energy being used every single second. To really understand electrical power, we need two key ingredients. And the first one is what I like to call the push. This is the force that gets all the electricity moving in the first place. The technical term for it is potential difference, but you and I know it as voltage. So what exactly is this push? Well, here's the textbook definition. Potential difference is basically a measure of how much electrical energy gets turned into other stuff, like the light and heat from a light bulb, for every little bit of charge that passes through it. Think of it as the energy toll a charge has to pay to get through a component.
I love this analogy. It makes things so much clearer. Imagine a tiny unit of charge is like a little person. Now the battery, the source, gives each of these little people a Lego brick made of energy. That's its job. Then, as our little person travels through the circuit and reaches the light bulb, they have to hand over their Lego brick to make the bulb light up. That moment of giving up the energy brick, that is the potential difference. It's the energy used up by the component.
And that Lego story perfectly sets up this formula. Voltage, or V, is simply the work done or energy transferred, that's W, divided by the amount of charge, which is Q. So if a battery gives 12 joules of energy to every coulomb of charge, well, its voltage is 12 volts. It's just energy per charge.
So we've got the push, the amount of energy packed into each bit of charge. But, that's only half the story. To get any real power, you also need movement. You need a flow. And that's what we're talking about next. This flow is what we call current, and we measure it in amps, or just amps. Now, we just mentioned charge is measured in coulombs. Don't let that word scare you. For our purposes, a coulomb is just a giant bag of electrons. I mean, a ridiculously huge bag. So when we say the current is 1 amp, it just means that one of these giant bags of electrons is flowing past a single point in a wire every single second. It's the rate of the flow.
And here it is. This is the big aha moment where it all just clicks. Power is what you get when you combine the push and the flow. If we multiply voltage by current, just look what happens with the units. We have joules per coulomb, that's our voltage, our push, times coulombs per second, that's our current, our flow. The coulombs on the top and bottom, boom, they cancel each other out. And what are we left with? Joules per second. And what did we say a joule per second was right at the beginning? A watt. It's just perfect.
So it all boils down to this incredibly elegant and, powerful formula. Power equals voltage times current. The rate you use energy is just the energy each charge carries multiplied by how fast those charges are flowing.
Okay, so the theory is neat and tidy, but how does this stuff actually work out in the real world? Let's put this new formula of ours to the test with a couple of real-world examples.
All right, here's a classic problem. We've got a lamp, we know the push across it is 12 volts, and we know the flow going through it is 3 amps. The question is pretty simple. What's the power of the lamp? How many joules of energy is it cranking out as light and heat every second?
We've got the tool for the job, right? We know that power equals voltage times current. All we got to do is pop in the numbers we were given. And there you have it. 12 volts multiplied by 3 amps gives us 36 watts. That means our lamp is chewing through 36 joules of electrical energy every single second it's on. It's really as simple as that. Now, this slide is such a great visual for why this all matters. On the left, you see a lamp hooked up to 12 volts. On the right, a similar one is connected to 240 volts. The one on the right is obviously way brighter. But why? Even if the current, the flow, was the same, the 240-volt lamp is brighter because each and every coulomb of charge is carrying 20 times more energy. It's a much bigger push. More voltage equals more power, and in this case, a whole lot more light.
Okay, so check this out, because it's a really fascinating little quirk. You'd think if you double the voltage, you'd just double the power, right? Makes sense. But nope. Because of something called Ohm's law, when you double the voltage, you also end up doubling the current. So when you go to calculate the power, you're multiplying two things that have both doubled. And 2 times 2 is 4. Doubling the voltage actually quadruples the power. It's a huge deal in electrical engineering, and that's why tiny changes in voltage can have massive effects.
So let's just step back for a second and wrap all this up. What are the absolute must-remember points from all this?
It really all boils down to this. Potential difference, voltage, that's the push. It's the energy per charge. Current, that's the flow. It's how many charges are moving past per second. And power, well, that's what you get when you multiply the push by the flow. It tells you the total energy being used every single second.
And that brings us right back to the very beginning. What does a 60-watt light bulb actually mean? Well, now you know. It means that for every single second that bulb is on, it's converting 60 joules of electrical energy into light and heat. The mystery is solved. A watt is a direct measure of how fast energy is being used.
So I'll leave you with this final thought to chew on. We just saw how a seemingly small change, like doubling voltage, can have a massive impact on power. So how does that fundamental principle shape the design of literally everything around us? From that tiny little box that charges your phone to the massive high-voltage lines that crisscross the entire country, this idea is everywhere. What else does it explain? Thanks for joining me.